Okay, everybody. We are still talking about functions, and we are going to talk about how we can combine functions, right? So I've got a couple of functions up here, f of x I've given as x squared minus 7x, and g of x is equal to 2x plus 1. So the idea is similar to with numbers, or at least that's where we're going to start, right? You can combine numbers to create new numbers, right? You can add the numbers 2 and 3 together to get 5. You can divide the numbers 36 and 9 to get 4, so on and so forth. So we do similar things with functions, and we can combine them with our 4 classic operations of addition, subtraction, multiplication, and division. So we can define a new function. Let's come up here. Call it h of x as simply the sum of f and g, right? So if I want to compute, for instance, let's say h of 2, it means I take f evaluated at 2, I take g and evaluated at 2, and add those together. So let's go ahead and do that. So f of 2 is 2 squared minus 7 times 2, or 4 minus 14, or negative 10. G of 2 is 2 times 2 plus 1, or 5. And so we get h of 2 is equal to negative 10 plus 5, or h of 2 is equal to negative 5. Okay, nothing too extraordinary there. We do sometimes want to write h a little more explicitly. What I mean by that is we can use algebra and the definitions given of f and g to write h out a little differently. So h of x is equal to f of x plus g of x. But f of x is simply x squared minus 7x, and g of x is 2x plus 1. And notice we can combine like terms here to get x squared minus 7x plus 2x is minus 5x plus 1. And here's an equivalent way to write down h. And let's notice h of 2 is equal to 2 squared minus 5 times 2 plus 1, or 4 minus 10 plus 1, which is equal to negative 5. And so our result is the same. All right. So we can, this is the definition, right? H of x is equal to this to f of the sum of f of x and the sum plus g of x, right? So if you evaluate each of those, to evaluate h of 2, you evaluate f of 2 and g of 2 and add them together. However, we sometimes shortcut it, as I've shown you here, by using algebra to write out the function h more explicitly. There can be a problem with this, and we'll do that in just a few minutes. But let's do one more example before we do that. Let's define another function. Let's just come over here where we have some space. Let's call it k of x. And I'll call it f of x times g of x. And let's do k of 2. And just as before, I can take f of 2 and multiply it times g of 2. So f of 2 we already have is negative 10. G of 2 is 5. And so we get k of 2 is negative 50, right? But we can also do the same kind of manipulation we did before, which is take k of x and instead of writing f of x times g of x symbolically, let's actually write out the expressions for these functions, and we can then multiply these two expressions. So we're going to get 2x cubed. Let's see, we'll get a plus x squared minus 14x squared, so minus 13x squared. And then we'll get minus 7x. Right? So here's another way we can write k of x. So write 2x squared plus x squared minus 14 minus 7x. Looks good. Then if we evaluate it at 2, we get 2 times 2 cubed minus 13 times 2 squared minus 7 times 2. So what do we have here? That's 2 times 8 is 16 minus 13 times 4 minus 14. 16, so 13, that's going to be minus 52 minus 14. If you work that out, we again arrive at negative 50. Right? And there are reasons you would do it the way in both of these. We did it in the first steps, where you might evaluate the functions first, each individual function, and there are reasons you would do it the way we did it in the second way, is where you might come up with an expression for this new function after using algebra to simplify a little bit. Either way is perfectly valid, except in one case. So let me remind you, the definition of, for instance, addition is to take the evaluation of each function and add them together. The multiplication is to take the evaluation of each function, the output of each function, and multiply them together. That part has to happen first before they're multiplied together. When we do this algebraic manipulation, we're kind of covering over that step, which usually doesn't have a problem, but can have a problem. And let's do an example now to show that. Let's rename these functions. Let's redefine f and g. So I'm going to take f as x squared minus 1 and g of x as x minus 1. Right? And I can make a new function now. Let's use division this time. So I can take the function h of x is equal to f of x over g of x. Okay. And let's do that algebraic manipulation we did. So h of x is equal to x squared minus 1 over x minus 1. If you notice what's going on in the top, when we notice these factors, we cancel them and we get h of x is equal to x plus 1. Okay, so now let's evaluate h for a couple of different values. Let's start with h of 2. So h of 2 is going to be f of 2 over g of 2. So f of 2, this is easy enough to do in our heads, x squared minus 1, so 4 minus 1 is 3, over x minus 1, 2 minus 1 is 1, so it's just 3. If we use this manipulation we have here to write x plus 1, we get 3 as well. So far, so good. The problem shows up when we have something like h of 1, right? So if h of x is equal to x plus 1, then h of 1 is going to be 1 plus 1 is equal to 2. On the other hand, if we use f of x over g of x, we get f of 1 over g of 1, but f of 1 and g of 1 are both 0. 0 over 0 is not defined. Oops, this is supposed to, sorry, I should have gone to a second line here. I'm doing too many steps in my head. So if we use this definition, which is really the definition, we have 0 over 0, which is not defined. So our function h is not defined at 0, though here we showed a result which shouldn't have shown up. The problem is in this algebraic manipulation, right? When we cancel factors, if a factor can be equal to 0 in the denominator, we have to be careful when we cancel it. The function here, or the expression here, is not equivalent to the expression we arrive at the end. These are not the same expressions. They're exactly the same for all values except at x equals 1, where the one on the left is not defined and the one on the right is equal to 2. So we just have to be a little bit careful when we do those manipulations, because the definition of combining functions, in this case through division, through a fraction, is that we evaluate each and then do division. If the denominator evaluates to 0, that division is not possible, even though that was hidden when we did our algebraic manipulation. So we have to be a bit careful there, right? And this makes sense if these functions are meaningful in the real world, right? We're just doing them as algebraic expressions and learning how to manipulate. But if that function g meant something, maybe this is supposed to give us some kind of ratio of I don't know, profits or something. If one of the profits is 0, you can't really take a ratio in the same way. And so this function doesn't really make sense, right? So if that 0 indicates that something's not possible, but we're still showing a result, that's a problem. Okay, all right, these are the basic ways to combine functions. We'll start a new video for our more complicated way that does not have the same kind of analogy with numbers, and this is composition of functions. So we'll see that in the next video. Thanks, everybody.